Hi, my name is Shankara Pailoor. I'm a research scientist at Veradice, and today I'll be presenting our work Picus, which is push-button verification of ZK circuits. And so this isn't work done just by Veradice, but also is a collaboration with our friends at 0xPark and C-Conduit. So as many of you know, we have seen a big emergence of ZK applications in Web3 space. So we have privacy-based smart contracts, roll-ups, and even privacy-preserving blockchains. And we at Veradice have done a lot of work auditing these applications across these very different domains. And to make our lives easier and the lives of other auditors easier, we've been building tools to help find bugs in ZK applications. And Picus is one such tool. So before proceeding, I'll briefly go over the general workflow of building a ZK application. So at the heart of every ZK application is a circuit, and this circuit will typically be written in some domain-specific language like Circum or in a framework like Halo 2. And these kind of have two components. The circuit will get transformed into two different components, one which we call a witness generator, and another which is going to be a set of polynomial equations over a finite field. And the idea is that you can use some proof system to take these field equations and construct a prover and a verifier, and then at runtime you would use the witness generator to produce witnesses and generate proofs. And the idea is that when you're auditing these systems, the source code is going to contain both the computation as well as the constraints. And ideally, as I'll get into that in a bit, but before going forward, I'm going to just briefly show you an example in Circum. So here's like a very simple circuit in Circum. It's a template technically, but here you have two input signals, AB, two output signals, and these three lines of code describe both the computation and constraints. So the computation is going to just do two things. One is a field division. The second, which sets the first output to as a field division. And then the second one is going to be the sum of the inputs. And then the constraints basically enforce the same thing. And then, as I mentioned before, at runtime, you would get some inputs, execute the computational part, produce a witness. And the idea is that ideally, there's some caveats before I say this, but the computation and constraint should be equivalent. And I'll define what I mean by that more precisely. So basically, so you're given some program P, takes inputs X, produces an output Y, and a set of constraints C over inputs XY. Ideally, you'd want for every XY pair, if P of X equals Y, if and only if C of XY is true. So ideally, you would want basically the only satisfying assignments to your constraints to be those that are produced by your computation. And at Veradice, we have found many, many different ways that this equivalence can be violated. And I'll talk about one today, which is under-constrained circuits. So more precisely, we say a circuit's set of constraints C here are under constraint if there is some input X and multiple distinct outputs Y, Y prime that both satisfy the constraints. And the reason this is kind of bad is that essentially what this means is that your verifier is going to accept some witness that doesn't actually correspond to your computation. And in practice, a lot of serious ZK hacks have been due to under-constraint bugs and resulted in severe financial loss. So to make things more concrete, here's like a very simple example of an under-constraint circuit. So if any of you have worked in Circum, there's a template called Numb to bits. So this is an intentionally buggy version of that circuit. So what this circuit will do is it'll take some input signal, some integer value in the finite field, and output its binary representation as an array of n bits. And so the reason the circuit is buggy is that the loop condition iterates over the first n-1 elements instead of all n elements. And so when this template is instantiated with n equals 3, so you only have basically a bit vector of length 3, the last element in the array is completely unconstrained. So no constraints are generated for that bit. And so that means that an attacker can basically pass in any value they want. So now there's basically two strategies, broadly speaking, two very simple strategies for detecting under-constrained bugs in circuits. One is what we call static analysis of these constraints. Essentially, you start with a set of predefined rules, and then you use those rules to prove that signals are uniquely determined by the input. So for example, suppose you had a set of constraints like the one on the left. The rules might say something like this: since z is a function of x and the output y is a function of both x and z, then we can infer that y is actually a deterministic function or a mathematical function of x. And so we know that it's uniquely determined by the input. Another strategy is using something called SMT reasoning. So basically, under-constraintness can be expressed as a formula in first-order logic. And basically, if this formula is satisfiable, that means that the circuit is actually under-constrained. And so there's two trade-offs between these two approaches. First, static analysis is highly scalable. You can actually analyze very large circuits and prove they are under constraints, but in practice, they have a lot of false positives. In order to scale, you have to do a lot of approximation. Now, SMT reasoning, ideally you can be as precise as you want, and actually you technically have a decision procedure for determining under-constraintness, but the downside is it's very hard to scale, especially because we're working over these finite fields with very large primes and lots of constraints in practice. However, we found that these two approaches are actually quite complementary. And so with that insight, we actually built a tool called Picus. So Picus takes as input the set of field equations, and it actually works in an interactive loop. It has both a static analyzer and an SMT solver, but the idea is that these static analyzers and SMT solver actually share information interactively in a loop. And so that allows both to make progress when the other is stuck. And the idea is that the information shared can make each other's lives much easier. And so Picus will then output a green check if it can prove, meaning that we have a certification that all the output signals are uniquely determined by the input. So we call that properly constrained. Red X, if it can actually prove that the set of constraints is under constrained. And then we're going to call this question mark if it cannot. So as I mentioned before, technically we do have a decision procedure, but in practice, because solvers can take a long time, we have a timeout, and so we return a question mark. So there's three key insights here. First, we're really combining the strengths of both static analysis and SMT-based reasoning. And we do so by having these phases interact in a loop. And the idea is that the partial results from one can help the other, and vice versa. So I'm going to talk about each phase in slightly more detail. So we have the static analysis phase, which we call this uniqueness constraint propagator. Takes as input the field equations along with a set of signals, K, which the procedure has already proven unique. And the idea is that at the beginning, the algorithm has K be the empty set, or technically just the input signals. And the idea is that this uniqueness constraint propagator is going to output a set of new signals K prime that its rules have determined are actually unique. And the idea is that if all the output signals are a subset of this K prime, then we know that our circuit is properly constrained. Otherwise, what we do is we send K prime, these new signals, as information to the SMT phase. And so we call that the semantic reasoning engine. So similarly, it also takes the constraints as well as these signals that have already been proven unique, and it outputs two things, which we call K double prime new signals that are proven unique, as well as signals that are proven to be under constrained. And the idea is that the input K prime can be used to actually simplify the formula that we give to the SMT query. And similarly, we have the correctness condition is the same as before. If it turns out that if the reasoning engine says that there is an output signal that is under constrained, then we can return this red X. And then if within the timeout no new signals have been proven unique, then we've reached a fixed point and we return unknown. And then if we have found new signals, then we kind of pass that back into the static analysis phase and repeat. And so here's how the kind of loop works as a whole. This is the big diagram. I'm not going to repeat it. But we actually published a paper at PLDI this year describing this in a lot more detail, like what rules we used and stuff like that. And so please check out our paper. So going back to this num to bits example, I'll just show you what Picus produces when we run on that example. So recall this is the buggy implementation, and on the right is going to be the output that Picus produces. So here you can see debug information that corresponds to like the uniqueness constraint propagation. So it's applying these different rules, and it found like some signals that it knows that are uniquely determined by the input. Then it passes those to the SMT phase. SMT runs the query, and it finds an actual counterexample. So the output's a little bit uninterpretable, but trust me, that's an actual counterexample. All right, so to evaluate Picus, we collected, so to both evaluate Picus and to also have, to facilitate more development in this space, we curated a set of benchmarks from Circum lib, which is like one of the standard library for Circum. Circum is one of the most popular languages for writing ZK circuits. So it has 163 circuits. And we kind of broke up this data set into two individual benchmarks, one which we call the Circum lib utils. So basically, this is a utility templates for fixed width integer computation, as well as some blockchain primitives. And then with another one which we call Circum lib core, which is pretty much I think it's like the 50 most security critical templates in Circum lib. And so here's some aggregate statistics about the circuits. So they kind of vary quite wildly in terms of the number of constraints, but I think we tried to design them to replicate real world usage. And so I'm going to summarize some of the results from our evaluation. So we found that Picus was able to successfully prove that 101 out of the 163 were properly constrained. We did manage to find 8 under-constrained circuits, and we have reported all those under-constrained circuits to developers, and the fixes are under review / under discussion. And so now to conclude my talk, there's 2 main takeaways. Basically, we have a tool called Picus. It's a fully automated tool to verify and find under-constrained bugs in your circuits. It leverages static analysis and SMT reasoning in a synergistic manner. And we have actually made our tool and benchmarks completely open source. And here's our link to all our socials. And now I'm happy to take any questions. Oh, okay.
Hi.
Hi.
I'm Miguel from Surfer Monkey. So we do privacy preserving techniques. We have circuits with Circum. How can we test it?
Are you asking how can we use our tool?
Yeah, how can we use Picus?
Well, actually, we have our GitHub link here, and I think we do have instructions in our README for how you can use it. So Picus currently takes the R1CS format as input. It's not a fundamental restriction, but that's just the current implementation. But if you can pass it the R1CS file, then it should be able to like automatically run on the circuit and determine whether it's under constraint or not.
What's the average time for like a circuit?
Okay, yeah. So we found among the circuits that it can certify, I think it was like 18 seconds on average. It's going to depend obviously on the size of your circuits. So I think it could be anywhere from 18 seconds to a minute, but there's timeouts. If it's more than a minute, then it's unlikely to ever terminate. So, but you can configure the timeouts, obviously, and we're obviously happy to help you if you have any issues with it. And yeah.
Yeah, hi. Yeah, really exciting work. I'm Junda from Cellular Network.
Okay.
We did extensive ZK framework benchmarking across different frameworks. My question is exactly about the timeout part. Looks like there is no guarantee your loop will always make progress, right? Your K and K prime, there's no guarantee it's always getting...
No, there's no guarantee, yeah.
That's not like my major concern. Like for some of the circuits we generate is like 40 million constraints. How do we do
So
with
there's
that?
like, one thing you can use Picus, the way I presented it is you just kind of throw everything at Picus and then have it do it. That's not really a reasonable way to use tools in general. I think the way we like to use Picus is, when we do use Picus, is that we take like individual, like if your basically larger circuit is composed of several sub-circuits, then what you can do is like pass in maybe components to Picus, learn some information, and then, you know, kind of do this in a more modular way, rather than giving everything all at once. I think that's generally probably the best way to do it. Yeah.
But there is also no way inside your framework to detect, oh, I'm not making progress for this case.
Oh, no, we actually, so I think what we do, because what we will say, I guess the way we determine no progress is if, like, you know, there's some kind of timeout, like within the solver or, yeah.
But in every iteration, you could see have you gone better or not.
Yeah, so if we, so the idea is that, so if we observe a fixed point, then there's no way, then we can prove that there's no more progress that can be made, because, you know, the solver will take the same amount of time every iteration. But yeah.
So did you, from, sorry, so in your example, there are like out from 160, and you prove 101, and then there are 8 negatives.
Yeah.
The other remaining, did you find any common pattern that could cause the
Yeah, one thing we've observed is that actually the bit, so first of all, the timeout is still due to the solver. I think while the solvers are, we're currently using a very prototype version of a finite field solver, which is specialized to for this domain. But it's a very like new prototype, and so it still times out even with all this help from the static analysis. Some of the reasons I can talk to you offline about why it actually slows down, but yeah.
Thank you very much. If you have questions, please take them outside. We have our next speaker right now. Thank you.
Thanks.